Okay, so should I start?
Yes.
Well. So let's speak a bit about lubricants and relaxometry. So first, we try to define what is an ICE lubricant. ICE means the internal combustion engine. And the main functions of a motor oil or a lubricant, engine oil or engine lubricant or whatever, there you can refer to them in many different ways, is to reduce friction and wear. Is also used to cool specific part of the engine, to keep clean the internal part of the engine, and to prevent rust and corrosion. These are the main functions. Of course, there are others. So what is a lubricant at molecular level? It is composed by a base, which is the main part of the lubricant, about 80–90%, which is composed of a blend of hydrocarbonated molecules between 18 and 40 carbons, more common lubricants. And this base can be a mineral base, just coming from a distillation of crude oil, or a synthetic, can be synthetic, fully synthetic even. And the other part, important part of a lubricant, is the additive pack, where we can mention as one of the main important, the viscosity modifiers, but also antioxidant, detergents, dispersant, pull point, etc. This is related to the temperature at which the lubricant is not flowing anymore. So these are the kind of molecules we have in the blend. And for a lubricant, for the function they have, branched molecules are much more efficient in tribological terms than linear molecules. So the lubricant, once in use in the engine, starts a degradation process that is mainly driven by heat, additive depletion, and contaminants, because you have solid residuals that start to accumulate in the fluid as a result of the combustion, for example. And this is changing the lubricant properties with time. So the critical test here is, or are, better to say, tribological performance tests, where you can really quantify the efficiency of the lubricant, but refer to the friction between surfaces. So you can analyze under a given pressure when the lubrication properties are broken and you have friction. This is the central point in tribology. Yeah? Is how the friction coefficient depends on the Hertzheim number that is given by the viscosity of the lubricant oil. This is the property, specific property of the lubricant, but also depends on the velocity, relative velocity between the surfaces and the fluid. And of course, the pressure, the load, the pressure between the surfaces. So then you may have different regimes. And this is the essential point here, is that the lubricant is only a part of the problem. There are a lot of tests that have been, for example, different norms delivered by American Society of Testing Materials. These are all standardized techniques to analyze the properties, different properties of a lubricant. There are others, and specifically, most of these techniques are physicochemical analysis, but I insist that the tribological performance of the lubricant, these are also very important analysis and are even normalized also. So let's go to something closer to us, spectroscopy. And let us compare a little bit FT-NMR and FT-infrared. So infrared in 1949 was in principle the first spectrometer that was attributed to Peter Felget in UK. And 20 years later, appeared the first commercial instrument, and this was in principle done by DigiLab in the USA. DigiLab still exists. It's a company that was taken by a big one, but they still exist. NMR dates, okay, NMR people, I hope more of you are NMR people, you know the dates. The point is that the first Fourier transform NMR spectrometer, as far as I could find, was appearing in 1972. So we can fix 1973 as a reference date where both techniques were already established and well known. This is a silly thing I did just to see what happened. I put in Google Scholar this change of words. Here, the infrared spectroscopy, here NMR spectroscopy, and the different, I analyzed the different periods of 10 years. You see the first period of 1973 to 1980, only 5 events for infrared. Here you count papers, patents, and citations. NMR, you have a much larger number at the beginning, but this is because, I hope, a lot of works here still were using continuous wave NMR, okay? But not here. Here, I should say that mainly spectroscopy refer to the spectroscopy as we know it today. But I want to show you this point. This is the year 2004, when the infrared spectroscopy was normalized, was adopted as a technique and accepted for different studies, different norms, for the quality control of lubricants or for the design and so on. And this was, in my opinion, a big motivation for the increase in the quantity of work using this technique. This did not happen in NMR, okay? What about if you go to relaxation and relaxometry? Okay, you see the numbers are much lower. And here, if we go to relaxometry in particular, I should say that this increase here is mainly due because in the last 20 years, any kind of NMR experiment where relaxation times or rates were measured were called relaxometry. But at the beginning, relaxometry was specifically referring to relaxation time experiments as a function of a time scale. For example, field cycling NMR relaxometry, T1 roller relaxometry, etc. Anyway, you see that relaxation relaxometry are far away from this number, still today. So if I had to try to explain this, okay, Fourier infrared is depending on a compact hardware which is not very costly. Very complex instruments here are about $100,000, $150,000, no more than that. And at the beginning, they had the possibility to get the spectrum very fast. In contrast, NMR has a complex hardware, high cost instrumentation, large instruments. You need a big room to put the magnet, and so on. So this eventually was also a reason against the adoption of the technique. And if we go to relaxation relaxometry, we have a problem that is this one. First, we have a double model dependence. It's not a direct experiment like in spectroscopy, where you have a spectrum, and if you are expert, immediately you know what is going on. Just look into the spectrum, in the screen of the instrument. Here you need an external data handling, of at least today still is like that, but this double model dependence is a main point. Okay, so now I would like to refer to this experiment we did in 2005. That was the first experiment, as far as I know, using field cycle NMR relaxometry in an engine motor oil. And what we find out in this work, we wanted to just to see mainly the detection capability of the technique for this application. And we were surprised somehow. We saw that it was more sensitive than infrared spectroscopy. Here, what you see, this is our two different engine oils. This was used in a truck engine, and this is a car engine, different oils. It doesn't matter the details of the degradation. This is a very complex process because in engine, you have many different ways in which that are working in parallel for the degradation of the lubricant. But the point, and I want to show you, and I want to stress from now, is that the sensitivity, the highest sensitivity, is reached at low frequencies. Okay, this is an important point. Concerning the fitting model, this is not the essential topic of this talk, but I want to stress the fact that such a simple model like a Torre term for the account of the diffusion of the molecules, plus a BPP term, let's say a Lorentzian term for the account of molecular rotations, was enough to explain the dispersion, okay? So this is the essential point here, sensitivity. Look what we have gel oil here, for example, and what we have in the infrared spectroscopy, the sensitivity is very weak. Of course, we can recognize that here we have some maybe sulfating problem here, we have oxidation and so on. This is the main advantage of the spectroscopy. You immediately can know what is going on and which is the responsible, yeah? With relaxometry, we do not have this. Anyway, the sensitivity here is quite low compared to free cycling the same oil. So as a main result of this work, I should say, at least in what sensitivity concerned, it was promising, free cycling as a technique, but we have the problem of the interpretation. Okay, we can explain the dispersion, we have a diffusion, a rotational, and so on, but we have to translate this to essential things that are happening there, and this is the difficult part. So for 13 years, we practically did nothing with that, but nobody did also. I can say that some works appear in between using free cycling NMR relaxometry in food oils, but not in lubricant oils, not engine oil. So after 13 years, we came back, and now we started to analyze, just try to do some more controlled experiments. So we went to the base, not the lubricant, just the base, and a controlled degradation in the laboratory, not in an engine. And we choose a controlled degradation that is important in an engine. It's a thermal degradation. So we choose two temperatures, 90 degrees and 270 degrees. So you see here the results, the dispersion curves are very similar, like before. And you see here the fresh oil, green. This is the degradation at 90 degrees over 1000 hours is the black, yeah? And the red, just 17 hours at 270 degrees. So what we see here is that essentially 90 degrees over 1000 hours are not very important in degrading the base. Just remember that here we do not have the additive pack. It's just a mineral base. Here we have a strong change in the relaxation rate. At this degradation is not a long time, but higher, much higher temperature. And the experiment was done not only at 30 degrees, but also was done at 75 degrees. What we find out is that at the lower temperature, the sensitivity, that is the difference between degraded and fresh samples for 270 degrees Celsius, is much important at the lower temperature. So at which temperature we measure is a point here. And concerning the model here, we replace the Torre model by this other free force hard field model coming from Fried, but it's also a very simple model for mainly we are thinking in spherical molecules and so on. But you see the explanation of the dispersion, for the explanation of the dispersion is working very nice. Okay, so now we see the relative contributions of the diffusion with respect to the rotational BPP term. And we see that diffusion is dominating, at least for this case. So in addition, we have that there is a frequency region where this spectral density is not dispersive, so we can replace here by a constant, and we can run a kind of simplified model, and this comes as a function. I want to close this. Yeah, as a function of the root square of the frequency. Okay, so if we plot this as a function of this, from the slope of this line, we can get the diffusion constant. Okay, so we do this, and you see here that we can see a difference in the diffusion constant only when we degrade at a higher temperature, but not at 90 degrees. This is in relative terms. After normalization, 1 is the diffusion coefficient corresponding to the fresh oil. So this is degraded at 90 degrees for 1,000 hours. There is practically no change, but it comes to 1/2 for a short time degradation at 270. And if we run the same experiment at 75, so here there is no important or relevant change in the diffusion. And this is a straight line over the wall frequency range. That means that diffusion is dominating in all the range. So the point here is this. This is the main point. The temperature at which we measure turns critical in this relaxation experiment. So we may say that the degradation of the oil, it may be obvious, but okay, we can see it through relaxometry. It's not, it occurs once the oil comes into the cylinder, yeah, during the combustion, where the temperatures can rise or be even higher than 1,500 Celsius. So the transient temperatures are very high. The oil is in contact or subjected to this temperature a short time, but every cycle of the engine, a part of the oil is going there and degrading and so on. So now we switch the point. So far in the data I show you, we have analyzed the magnetization evolutions of the relaxation in terms of mono-exponential function. But when we started to do experiments also with T2, we could see that, and also diffusion, T2 and diffusion, they show multi-exponential character, much more evident in T1. And then we have to analyze different ways for the analysis of this. And okay, you know, there's different possibilities: inverse Laplace transform, stretched exponential, multi-exponential fitting, log normal distribution, etc. However, all of them, you can find one limitation at least. In the case of ILT, you know, this is very successfully used. It was successfully used in the analysis of in porous media, for example. But the problem here is that there is a dependence of the smoothing parameter. And sometimes when you want to extract specific quantities from the analysis, this may be a problem. It is also sensitive to the noise. Okay, and so on. The stretching, you have the stretching parameter that sometimes is difficult to interpret. It's a multi-exponential fitting you cannot do if you have several exponential decays or a distribution. It's not useful at all. And log normal has some numerically complex integrations in between. Then there is a work in 2012 by Reding and other people that they analyzed the possibility of the gamma distribution, but they were pointing mainly to diffusion, but this can also be used in relaxation. It's the same. So this R here may be a relaxation rate or a diffusion constant. But the point here is that we had to move from this mono-exponential decay to this. That is a distribution of relaxation rates, decays or growth, depends on what you measure. Of course, this can be adapted for any kind of exponential formula. So the gamma distribution is like this. Kappa and theta, two parameters. Kappa is the shape factor or shape parameter, and theta is the scale parameter. And once we replace this into the integral, the big advantage of the gamma distribution is that you can solve it analytically and you get this. And there is a relationship between the mean value of the distribution, that means the mean value of the relaxation rate, for example, or the diffusion constant, in terms of these parameters, and also the width of the distribution. So that means that the physical interpretation is very simple for this distribution. And then you can write the magnetization evolution in this way. So these people from Karlsruhe, from the kit, they use it for the first time, as far as I know, in engine oil. And this is it's a T2 CPMG experiment. And the arrow, the red arrow, is going from the fresh oil to the most used oil. So the degradation makes the distribution of the main T2. The main T2 is shorter. No? So you see the distribution, the mean value is shifting to higher relaxation rate values. And also the width of the distribution is increasing. So we started to collaborate with this group in 1917, at the end of 1917. And we analyzed a lubricant, as engine oil that they had there in Germany. And you see here, depending on the runtime of the oil in a new engine, that was a new engine, a test engine, a fresh oil, and as you degrade the oil with aging of the oil, the relaxation rates increases in all the frequency range, and again, the maximum sensitivity is at the lower frequency. This shows the dispersion as a function of the time of use of the lubricant in the engine. When you have the change oil in the engine, and so on. Okay, and then we did the same experiments in the T2 analysis CPMG in these oils, and we reproduced the result they already had before with other different lubricants, and okay, the behavior was exactly the same. You see, T2 becomes shorter when the oil degrades, and the width of the distribution, that means the distribution of T2 values increases. Here in this plot, the point represents the mean value of the distribution, and the bar represents the width of the distribution. So you see, as you use the oil, relaxation rate R2 starts to increase, change oil, again decrease, and so on. And when we measure diffusion, exactly the same. Diffusion tends to decrease with the use of the oil in the engine. Again, the point, the mean value, and the bar is the distribution. Okay, so here we compare the diffusion constant, a microscopic entity, with something macroscopic like the inverse of the kinematic viscosity. And we have the Stokes-Einstein relation. And you see that if we plot with the inverse of the viscosity, then we should have, if everything is constant, a straight line. So more or less, this works fine, with the exception of the new oil and the most degraded oil. So something happens over a certain level of use that makes the oil is departing from this behavior. And by the way, you see this equation in principle is thought for spherical molecules. So a branched molecule is not linear alkanes on this kind of molecules we have in the lubricant somehow can be considered like some spherical or quasi-spherical entities. Works more or less well here. Okay, in this second work with this group of Karlsruhe, this is fresh. You see, it will appear next year, the paper. So we compare now a mineral base with a full formulated lubricant using that base. So including the additive pack. And okay, you see here in using spectroscopy, you can see very well, quite well, the effect of the thermal degradation. Again, this is for both, we use 17 hours at 270 Celsius. Clearly, you can see here the effects. These are mainly oxidations. And not in the lubricant, so the additive pack is very effective here in preventing the oxidation of molecules. You see, this is the lubricant with the pack, and this is the base. Yeah. Okay, this is the same, exactly the same, but it's shown in a different way, just integrating the spectrum in the different spectral regions. So you see strong changes in the base and no changes practically in the lubricant with the pack, with the additive pack. So we can say that the additive pack is fully active here, even after the 12 or 70 hours, sorry, at 270 degrees. So it was important degradation in the base, but not in the fully lubricant. So the pack is working. Okay, this is just which groups are affected in the different spectral regions. This is more a chemical analysis. I don't want to sometimes in here, but the oxidations seem to be the main things that happen to the base with this degradation and branching. And this will be shown later. This is an important point I want to show you. This is diffusion experiment using pulse field gradient measured at 400 megahertz. This point, this, and this, okay? And we see that there is just a slight decrease of the diffusion after the degradation. And now, this is the experiment I showed you before. And if we put the data of 30 degrees extracted from the field cycling analysis here, we extrapolate in this plot at 30 degrees, and they are located here. So you see the consistency of the analysis, even after using such a simple model we use to explain the relaxation dispersion, and the diffusion constant we extract from there. They're fitting quite well here. And the second point I want to stress here is you see the diffusion after this degradation is not changing practically nothing, just a minimum change. So the strong change observed here in the relaxation rate dispersion is mainly due to the rotational dynamics. The changes are mainly affecting the rotational dynamics for this kind of degradation of this. Okay, this is the same experiment, but for the lubricant, including the pack. So you see that practically there is no difference before and after the degradation. And again, the point represents the mean value of the gamma distribution, and the bar represents the width of the distribution. Here we show relaxation rates measured at different temperatures, R1 and R2, measured in a mini-spec instrument at 20 megahertz. You see, T1 is not sensitive at 20 megahertz, at least as a function of the temperature. There's no change, no important change here. This T1 is permanently somehow in a dynamical regime that is nothing is changed, but T2 is sensitive to the temperature. Here, the size of the data point represents the error in the determination of the mean value of the distribution. And the bar represents the width of the distribution. These are completely different things. This is the base, okay? Just to show you how we calculate the error of the mean value, this is the CPMG decay. You see the green line is the gamma distribution fitting. And this is an exponential, just to show you that the exponential decay is absolutely not working here. And to determine the error of the mean value, we just fit the upper points and the lower points not shown here. But then we have a range of potential T2 mean values. Here the same, but for T1, you see that the difference here between the gamma fitting and the exponential is much, much lower. So that's why fitting just with a non-exponential for field cycling data is not the ideal situation, but it's not so far from the gamma at the end. Okay, this is the same result as before, but now for the lubricant. It was before. So again, we have sensitivity in T2 as functions of temperature, but not in T1. And this is the important point I want to show you here. Here we compare the base, the fresh and the degraded base. Okay, you see that at higher temperatures, only started at room temperature and lower temperature, T2 or R2 start to have some sensitivity to the degradation. Yeah, this is an important point. So T2 becomes sensitive at low temperature. Look, which temperature? Okay. This is the relative change as the fresh and the degraded oils for T2 or R2. Okay, but you see that even when the mean values present a change at lower temperature, the error of this mean value is so high, you have an overlapping of errors here. So in metrological terms, this is a weak evidence. Okay, here we compare for the base and for the lubricant. You see, by the way, that for the lubricant seems to be a bit more resistant to the degradation, yeah? Because it's more close to a no change between degraded and fresh. Now, let's go to T1, and we do the same at 400 megahertz, but this experiment is fixed at 30 degrees Celsius. We do not measure as a function of temperature. We fix the temperature at 30 degrees. So you see no changes at 400 for both samples, at 20 also, no change, absolutely insensitive. But at 60 kilohertz, we have an important sensitivity here. You see the mean values are completely different. And again, the error now is much smaller. I show you that in T1, the case, T1 growing functions, the exponential behavior is, the gamma function is much more closer to an exponential behavior. And even when the width of the distribution is large, but the mean values are well determined, precisely determined. And by the way, we can see here that the difference is much higher, or higher, not much higher, but higher for the base than for the lubricant, including the pack, the additive pack, okay? But the point here is that we have sensitivity at room temperature. We don't have to go to low temperature. So here you can see the same relative plot for no sensitivity at 400, at 20, but a very important sensitivity at 60 kilohertz, okay? So this is a very interesting result. So we don't need to cool the sample. At low fields, we have a very nice sensitivity. Okay, one can explain this. We are somehow stick here to the spectral density formalism. So the sensitivity in T2 comes from the secular term. This is fixed because when you measure at high field, this is a constant, but this is not unrelevant compared to this. So somehow it's masking the sensitivity of this time. But when you use T1, you go to low frequencies, all the spectral density is sensitive to the processes that are going on in the large time scale. So that's why T1 is more sensitive at low field. This is another work. This was, it will be appearing in the next days in magnetic resonance in chemistry. Here we compare semi-synthetic Castrol magnetic, and we came back to the engine, the car engine. Okay. Again, we see that the fast degradation during the first 10,000 kilometers, and then seems to be that there is not more change in the next 10,000 kilometers. And again, the Fourier infrared gives information, more detailed information on what is going on. And okay, so this is a main point I want to stress as a point that is somehow, yeah, important because for several techniques, the samples should be prepared before the analysis. For example, you have to take out all the solid particles that are suspended in the lubricant by centrifugation or by solvent methods. Okay, solvent methods here are not allowed because you will change the chemistry of the lubricant for relaxometry. That could be catastrophic. But centrifugation, it's okay. So we show here, we compare the dispersion with and without cleaning for these solid particles, and we have the same. So that means that essentially the presence of the solid particles is not affecting the relaxation rate dispersion. And now we try to make a more clean experiment. We say, okay, a lubricant is a blend of a lot of molecules with different molecular weights, different chemical groups, different shapes, different everything. Let's try to see what happens with pure alkanes, even if they are linear, and in a lubricant we have branched alkanes, but just to see that we think under thermal degradation, the process should be the same. So branched or linear, the degradation process at the molecular level should be very similar. So we use a family of alkanes that are which Campbell numbers are coincident with those that are present in the blend in the lubricant. And you see here, this is the case of a pure N-octacosane degradation at 250 degrees for 2 hours only. We see the sensitivity we have in the relaxation rate after just 2 hours. And we see also strong change in the Fourier infrared here. And we can explain the changes as a decrease in the quantity of CH2 groups, okay, and an increase of CH3 groups. And this is an indication of molecular fragmentation and branching. So just 2 hours at this temperature are enough to change, to produce this kind of change. And of course, everyone is sensitive to these changes. But also we have the appearance of carbonyl groups. That means oxidation as another process that is important under heating of the sample. And also, this is also a reason of why R1 may be more efficient. So here we analyze different molecules with different molecular weights, just to try to understand which is the influence of the molecular weight and also the presence of oxygen. You see that, for example, here we have 18 carbons like here, but the presence of oxygen, then R1 is higher. And this is the degraded sample here. It's much efficient. Maybe the intake of oxygen here due to oxidation and some chemical changes in the molecules. And also, maybe there is an increase in the molecular weight here. So this shows that there is a dependence on the length of the change in this case. And okay, this may be a branched alkane at this moment. Okay, so just to summarize in the 3 main points of this study we did in the last year. So first point is that the spin lattice relaxation is highly sensitive at low Larmor frequencies, but at room temperature, and is more precise than R2 or spin-spin, even if measured at low temperature. Okay. If I would have to choose one of the 2 techniques, I go for free cycling. Not because I am a free cycle fan, but because of this, for this case. Second point, in lubricants, we use usually branched alkanes are much more efficient from the tribological performance of the lubricant. And somehow we can assume that we have a quantity of molecules that are not perfectly spherical, but somehow. So this is consistent with the user diffusion model, which actually are based on or thought for spherical molecules. And the Stokes-Einstein relationship that somehow is valid for a range of use of the specimens. And the third point is that thermal degradation is mainly due to molecular fragmentation, branching, and oxidation of the molecules in the oil. Of course, maybe the novelty here is not so high because with other techniques, this was already observed, but the novelty here is that we can see the change in the NMR relaxometry, and complementing with other techniques, then we can explain. Of course, there is a long way still, to end with a final analysis using NMR relaxometry about what is going on in the fine thing at molecular level in the lubricant, but as a technique for a fast testing of the degradation is very efficient because we can have a result in few minutes, and this is interesting. However, the model we have is already good enough, and I don't know, I really don't know at the moment how more or how far we can go with a more detailed model for such kind of samples. Okay, so it seems that relaxometry will finally have a limitation in this point. Okay. Well, I would like to thank for the main collaborations or collaborators of this work in the last years in Córdoba, Eustaquio Erro, Leandro Jarbino, and Carla Fraenza. Eustaquio and Leandro, they are chemists, physical chemistry specialists, and Carla is physicist. Now she is at the postdoc in New York City. And in the group of Karlsruhe, mainly Gisela Guthausen and Eva Förster. So I thank them for the collaboration. I think we will still do something more. It is already in plans. We will see what comes out, how far we can go, trying to put closer relaxometry as a analytical technique for lubricant oils. Thank you very much, and remember to change the oil of the engine of your car.
Esteban, thank you very much. I stop recording.